Alright, let's talk about you guys' final. So,
Is it a composite?
derivative composite, yes.
So what we have to
Not the limit stuff, but definitely derivatives.
What about limits or derivatives using the limit definition?
No.
Oh, thank God.
No limits using the derivative definition.
I wasn't gonna help.
No derivative using the limit definition, sorry. Alright. So, your final will consist of 3 separate parts, 2 problems each, give or take.
Ah, no. 2 problems. 3 times 2.
Nice.
So it's gonna be 5 problems
Alright.
total.
So, for your final, there'll be 2 questions relating to the first and second derivative tests. So determining curvature, determining minimum and maximum, determining increasing and decreasing, basic stuff. Most likely that'll be your final question, the big long question with multiple parts. But we won't work give you a single function, and I ask you to do all those pieces. So determine the intervals of increasing and decreasing, determine the relative mins and maxes, determine the concavity, all that stuff. The other 2 parts will consist of being able to do implicit differentiation and being able to do related roots. Now, let's go ahead and take a couple seconds today for each of those types of problems. We'll try to do 1 each, and then we'll review will be very similar to our test, and we'll have our test on Friday. Now, my plan is I will get you guys to take a peek at the test on Thursday. You can take a look at it, know what's on it, get ready for it. But on Friday, our actual test will take place.
Right.
Again, it'll be 6 problems, but that's 6 calculus problems. It's a good time. So, let's start with some basic stuff.
6 problems, right?
Okay. First thing. And reminder, you cannot be exempt for this final AP class. So, okay. Let's see. Determine the following. If f of x is equal to x cubed plus 6x squared minus 14x plus 1. Determine the following. Intervals of increasing, intervals of decreasing. Concavity, for both concave up and concave down. Determine relative mins, determine relative maxes across the entire interval. Now I'm doing this with a polynomial to keep it relatively simple for today, but the same concept could be applied if there was, for example, a trig function. If there was, for example, a trig function. Huh, weird. Okay. I swear I heard an echo. Alright. So we have, in total, increasing, decreasing, concavity, mins and maxes. And again, these all be relative mins and relative maxes. Okay. Let's remind ourselves of our basic properties. If I want to determine intervals of increasing and decreasing, what are my general steps? Take a derivative. Find critical values. Either positive or negative all around those values. Okay, what about concavity?
Second derivative.
Second derivative.
Points of inflection.
Point of inflection.
Positive and negative around them.
Very good. And mins and maxes?
Plus the first order test.
First order test. All right. Well, let's see what you remember. Here's our function. F of x is equal to x cubed plus 6x squared minus 14x plus 1.
3x squared plus 12x minus 13.
F prime of x is equal to 3x squared plus 12x minus 14. All right, and you said, what do we do with that first derivative?
Put it in the quadratic form.
I think quadratic formula is fantastic here.
Yes.
So, would you like to go to that?
Negative 12 plus or minus square root of b squared minus 4c, so 144 minus 4 times 3 times negative 14 over, 2 times 3.
Okay, let's do it. So, negative 12 plus or minus square root. All right, what happened on the inside?
Oh, I didn't have the answer. But I skipped all the steps. I just cheated. Yes.
To 84.
I don't know why I didn't do that.
Oh.
So one second, I'll do that.
You definitely did it.
Okay.
Over 6.
Well,
what-
160.
what?
And then you gotta add them together.
312?
No.
Say, never assume I'm right.
Oh, yes.
312?
No, okay.
Yeah. Michael's.
Look, I have the last.
He just assumes that I'm right. He has great faith in me. I don't understand it.
I do.
Okay. What is the square root of 312? Does it simplify any?
I don't care.
2 square root of 78? So negative 12 plus or minus the square root of,
Well, you can always
plus or minus 2 square root of 78
Yes.
over 6.
Take out a 2.
Take out a 2 from everything.
Yes.
That'll end us with negative 6 plus or minus the square root of 78 all over 3. Beautiful. So what do these two numbers represent? The positive solution and the negative solution.
Where the curve or where the what do you want the first derivative test? Yes, where the slope changes.
Where the slope could change.
Negative or negative.
Beautiful. So what do we call those?
Critical values.
Critical values. These are our critical values. Okay, so I'm going to build my number line. I didn't know they happened to go in a certain order. Negative 6 minus the square root of 78 over 3. Negative 6 plus the square root of 78 over 3. If you go into a calculator, remember, I just need numbers around these. I don't need like something crazy here. So, numbers around and in between. What am I choosing?
Choose one in the middle.
1 in the middle. So 1. 1 would be a good test value. I'm going to change that to a different color here. Let's go red so it stands out.
Negative 5 to the left.
Negative 5 to my left. And to my right. 5 works.
Oh, no, I'll mix that up first. It's actually supposed to be one on the right.
1 on the right.
Middle would be to the right. Yeah.
1 on the right.
It's 0.94 plus, so yeah, it's 1 on the right.
So we go in between.
I know, I'm failure.
So it goes in between. 3/4.
I mean, I can learn it. Like, 0? No, 3/4. I'm going for it.
Don't be that way. Okay, so we plug into our original function f prime of x. Plugging in negative 5, 0, and 1. It's tempting to look at all the work we did over here as like necessary work. It's just to find those two critical values so we can determine where it's going to happen. So we go up here and try to determine, based upon those values, whether they're going to be positive or negative slopes. So I plug in negative 5. Positive. Plug in 0.
It's negative.
Plug in 1.
Yeah, it's positive.
It is. Okay. So let's answer the first piece. Intervals of increasing and decreasing. Intervals of increasing, please.
Negative infinity to 0.
So negative infinity, that's the best infinity symbol I've ever drawn. Infinity to 0.
And then in union, negative 6 plus square root of 78 over 3 to infinity.
Wait,
Times 0.
the 0 needs to be negative 6 minus.
Yeah, that's
Yeah.
Always use the critical values as your boundaries. Okay? And intervals of decreasing.
negative 6 minus and then negative 6 plus.
Okay, well, we're going ahead and be in here. We ask the next question, which would be max and min. Max. Say again?
The
Square root of 78. Max? Is already done. Min.
-6 plus.
And how do we determine that from the information we have?
Because it goes from, your -6 minus goes from positive to negative, so it goes up and then down, so that's your max. And then your -6 plus goes down and then up, so that's your min.
Fantastic. And what's the name for that? What you just described.
First derivative.
First derivative test. Yes. Good. Good. Fantastic, guys. Well done. Okay. So this is all the first derivative. Let's go to the second derivative now. So our original function was f of x is equal to x cubed minus 6x, sorry, plus 6x squared plus 12x.
Minus 14x plus 1.
So I just go up there. Minus 14x plus 1?
So it's just 6x plus 12 for your second derivative.
See? So f prime, hold on, I'm just writing on my pieces. Jeez, why are you going so fast? F prime, we said was 3x squared plus 12x minus 14. And what did you say f double prime was?
6x plus 12.
All right. Concavity. Before I can answer concavity, I need to determine the points of inflection. Remember, these are the places where our second derivative is equal to 0. So we take our f double prime. So it would be 6x plus 12. That equals 0. And yes, x equals -2. So, test values around it. So there's my -2. My test values around. Give me some values around -2.
0 and -3.
Beautiful. Plug them in. What do we get?
You have -6 or -3 and then
So negative.
yeah, and then positive.
Beautiful. So where am I concave up?
-2 to infinity.
From -2 to infinity. So when the second derivative is positive. Where am I concave down?
Wait, that's opposite.
Wait,
It's
now it's opposite.
No?
Is it not? Wait, positive. Yeah, no, it's still not here.
Positive is concave up.
Where does it when you get mixed up? Like, what's
The most common one is when you think about the second derivative in terms of whether it be mins or maxes.
right?
That's right, okay.
If it's concave up, it's going to have a minimum there. If it's concave down, it's going to have a maximum. Okay? Concave down? Negative infinity, -2. So, guaranteed to be a style of a question on your test. I could also ask about the other things we mentioned, which would be critical values. I could ask about point of inflection. Be ready for all of them. And there'll be some that don't ask for half this stuff. You know, there's multiple choice questions, like normal. So there might be a question that just says, hey, what are the intervals make these and these?
I'll still give every single part.
Okay.
I'm doing the work. I'm doing it all the way.
Next piece, implicit differentiation. This is when I have a function where finding y manually is difficult or impossible. And so we take a derivative with respect to x of the y function manually. Here we go. Take a function like xy squared plus cosine y equals 3. We've spent 2 weeks now thinking about related rates, which is a track card. Okay? You have to approach these separately. Related rate questions are often word problems. They'll often reference time. Look for those clues. Implicit differentiation questions just say take a derivative, and it's not easy to do. Okay? This is one where if I had to take a derivative with respect to x, I can't get y by itself. Like, if I move the cosine over, I still have y in both pieces. If I try to factor something out, I can't factor the y out of the cosine. If I use an inverse relation to get rid of the cosine, I get y stuck inside an inverse relation. Nothing gets easier. I have to do it implicitly. Now, how do I do that for these kinds of problems? First, taking the derivative with respect to x of this function. Now you can either use y prime or dy dx. I don't like using y prime myself because I'm used to it, but dy dx also sticks out really well. So some people really love using dy dx because you don't. I can't tell you how many times this will happen. You'll have y prime, and I know it's y prime, but by the next step, I forget it's y prime. And it's just a y that I messed up on drawing. You have no idea how many times it happens. Well, you might. You've seen my handwriting. So, I'm going to use dy dx for this problem. Alright, let's start with the first piece. I have to take the derivative with respect to x of xy squared plus the derivative with respect to x of cosine of y equals the derivative with respect to x of 3.
So your x is constant, so it's just going to be a 1. So then you have 2y.
Be careful. These are being multiplied. Product rule. Gotta use the product rule.
I got 2xy dy dx plus x prime y.
I think you're correct. Let me double check that.
I never follow the lefty right like that. I just know derivative piece.
Alright, well, I'm going to check it just in case. That way I have it on the notes. Alright, so my right hand piece is y squared, which means y prime would be 2y dy dx. My left hand piece is just x, which means my left prime would be 1. Alright, let's do it. Left d right plus right d left. Left d right plus right d left. So right d left. Those common mistakes are stuff like that where you just don't think to use the right rules. The rules are there, they still work, but you just forget about them. Like for the next piece. So that's all the derivative of xy squared. Plus the derivative of cosine of y. Nope. You think the tangent.
Sine y dy dx.
Negative sine y dy dx is beautiful. Derivative of cosine is negative sine. The inside stays the same. Since there's something inside of it, I take the chain rule. Derivative of y is y prime or dy dx. So my plus a negative is just going to become a minus sign. And then what's it going to equal?
0.
How do we know it's 0?
Because it's a constant.
Because it's constant. Derivative of constant is always 0. All right, what's my goal?
y dx by itself.
Man, the chorus of happy little minions over here is just going great. How do I do that?
Algebraic. Or is it arithmetic? I don't know.
Just who cares? How do we do it? I do math. Math. Do it then.
Subtract your y squared.
Perfect. Great first step. 2xy dy dx minus sine y dy dx. Some people will forget that piece. I don't know why. Minus y squared. Okay. Then
Dy dx out.
factor dy dx out. So I take the dy dx out. Dy dx. I end up with 2xy minus sine of y equals negative 1 squared.
Divide by your 2xy minus y.
And then divide, getting dy dx, and there's my answer. The negative y squared over 2xy minus sine y. Now, other questions I can ask, don't forget, since these are all derivative rules, I could ask for the derivative, which is done. I could ask for the slope at a specific point. Okay? I could ask for the slope at a specific point. Alright? I could ask for the tangent line. I could even ask for the normal line.
Yes.
Do not forget, those are all viable questions. Okay? Oh, but I will. I enjoy the torture so much. Okay, I'm going to put the original equation up here just so we can see it, because I like to see it. How much time though?
You know, you should just cut the time that we take the test in half. We have to start from No.
I don't know why I found this one so fast. I just do.
It looks like one of those laser swords. Very
Well. Alright, well that went there. Okay. So, beautiful. So we've seen implicit differentiation questions. We've seen questions involving your first and second derivatives using points of deflection, points of critical values, concavity, increasing, decreasing, all the fun jazz. Last piece is related rate questions. Odds are, if I had to tell you what the test is supposed to look like, there'll be 4 multiple choice and 2 free response. One of the free response, related rate question. Similar to what one of your homework problems would look like. Okay? So, were there any questions about the related rate stuff? I did homework with you yesterday, but if there was still a problem that we were still having that we couldn't get a solution to, we do have a few minutes left in class, about 8. I'd be happy to answer any we can. Or the extra ones I posted by request.
Oh my God.
They are tough.
Alone.
They are tough. I will tell you that. Like, there's no like nice way to put it where I'm like, oh yeah, they get easy. No, they don't. They don't ever get easier. Word problems are word
I
problems.
spent 3 hours practicing.
Like, when you choose not put one of the ones with like the included triangle, do you not put that
Wait, but kind of some easy
rare
ones.
shape?
Or for the love of God, please. The easy ones,
No,
you just
not
use
really.
the
You don't like doing the distance formula one like 4 times? I enjoy the distance formula one like 4 times.
No, I don't.
Oh,
Yeah,
okay.
and then the triangle, like if you have to.
No, we do the triangle.
Okay, I will finish today by looking at a related rate question and doing it in a slightly different way. Here we go.
I just use the Pythagorean theorem for all the sides. Just to find the sides.
Okay. I told you guys in the video last night, or yesterday I should say, that there was a optional, like, different way you could approach some of these problems. That's like, it's very creative in how you do it. And what you do is you do a related rate of a weirder formula. So, for example, the distance formula, the common distance formula is this formula. D is equal to the square root of, let's do the common version we used, which was x squared minus or plus y squared. Right? A variation on Pythagorean's theorem. However, this formula, which is Pythagorean's theorem, the other version of the distance formula, can also do a related rate for it. The only weird thing is I have to use this in my answer. Take a look. I'm going to start by doing a related rate problem to this other formula. So we saw before, last week, how to take this with respect to time, and we ended up with this equation that looked like this. We ended up with, on top, 2x dy dx, or sorry, dx dt, plus 2y dy dt, over 2 square root of x squared plus y squared. Like, this is the kind of nasty formula you end up with. The 2's eventually cancel. Like, that's just the form it gets into. There is a way to get that same solution with that other formula, which I think is easier because I don't have to do the chain rule. The chain rule for most students is the hardest one to do correctly every time, especially with implicit differentiation, especially with related rates. And so if I can avoid the chain rule by doing some creative math, I will. Here's how. Take a look at the bottom equation. Let's do it. So, d squared equals x squared plus y squared. Let's do it. So first, I'm going to split it into 3 parts. I'm going to do d dt of d squared, d dt of x squared, d dt of y squared. Okay, so far so good. Now what do I do? Well, the left-hand side. I would do, so the derivative of d squared would be 2d times dy, dt. Which, remember, is what I was looking for in most of those problems. I wanted to get this term by itself. Equals. So the derivative of x squared would be 2x dx dt. The derivative of y squared would be 2y dy dt. Well, if I want to get dt by itself, all I have to do is divide by 2d. That makes a lot of sense. So I'm going to do that. dt is equal to 2x dx dt plus 2y dy dt all over 2d. But remember, we know what d is. D is defined right here. So what I can do now is I do a simple substitution. Where everywhere there is a d, I replace with the square root of x squared plus y squared. And I end up with d dt is equal to 2x dx dt plus 2y dy dt over 2. Instead of d, I write square root of x squared plus y squared. And look at that. Exact same equation. Me too. Like, me too. Hashtag. Okay? Like, it's terrible. But it works. And here's the thing. Like, what I'm basically doing is I'm manipulating the equation. Now, this works really well in specific cases. One, when you can get the variable by itself, like d is already by itself. If I didn't already have an equation for d, now I'm stuck doing an implicit differentiation with 3 variables. Ew. Alternatively, if like you're raising something powered as opposed to reducing something's power, square roots present cases, right? Positive and negative. That makes it more complex. Squaring something reduces cases. 2 squared becomes 4, negative 2 squared becomes 4. It reduces the number of cases that get the same number of solutions. And so it actually makes it easier if I'm squaring things to do this way than if I would have to square root things to do it this way. There's a lot of subcases and pieces around this. So, like I said, implicit differentiation and related rates, they tend to be the harder problems just because they have to use all the rules, but they are great for review for your final. Were there any questions?
So are we having an actual review of this?
Yes. And it will look much like your final.
Exactly like our final?
Your review will not be multiple choice. Your final will. Does that make sense?
Yeah.
Okay, I will not be here Thursday.
Okay.
If I come in like 4 o'clock or something to look at what.
I will. Yes. 4 o'clock? Yes.
I'm just in the school for it.
Okay. Other questions?
I'll be here like I just want to get like the first part of it. I won't be here like the second half for I think.
Okay. We got like a minute and a half left.
How was your day off?
Okay.